In the previous video lesson, we have learned what matter is all about. However, while you were trying to understand what matter is, did you ever ask yourself of what this matter is composed of? In life science, it is discussed that our body is composed of tiny building blocks called cells. Yet, these cells are not the tiniest in the world. On our previous video lesson, we have discussed about the changes in phase of matter. Let us have a review of what we have learned last time by means of a game. I know that you are familiar with this. It is called 4 Picks, 1 Word. On this game, all you have to do is to guess the magic word or the word by using the 4 pictures as your clue. Let us try this one. If your answer is melting, then you got 1 point. Number 2. Very good. The answer is condensation. Third word. Alright, the answer is evaporation. Word number 4. We have sublimation. And for the final word, very good. The answer is frost. Let's take a look on this picture. Perhaps this picture looks familiar to you. Can you think of something that looks like this? Do you know the reasons why you usually see this as one of the symbols of science? Atoms are the building blocks of matter that make up everything that we encounter every day. Your ball pen and its ink, the page of your book or of your module, and even your body is composed of atoms because you are considered as matter. Even if we cannot see atoms, without the aid of the microscope, we can still represent atoms using ourselves. From the time the word science was introduced, many people gained interest with the things around them and became fond of asking questions about their surroundings. Up to this time, scientists never stopped investigating things. The history of the study of the atomic nature of matter illustrates the thinking process that goes on in the philosophers and scientists' heads. Some early Greek philosophers have played pivotal roles concerning the atomic structure. On this video lesson, we will compare and contrast the early ideas about the atom with the modern atomic theory. So we will talk about the atomic models and theories. The earliest direct evidence of the existence of atoms came from the work of a botanist from Scotland, Robert Brown. While observing pollen grains in a drop of water under a microscope, he noticed that the grains were in a state of constant motion, moving and jostling about. At first, he thought that the motion was due to moving life forms. Later, he found out that even non-living objects, such as soot and dust particles, showed the same motion. This constant jiggling of particles, now known as Brownian movement, is caused by collisions between the molecules of the suspending fluid. In the case of Brown setup, those of water. which are in constant random motion. Early scientists like Democritus, who were wondering if there was a basic building block for matter. Democritus introduced the idea of the atom as the basic building block of all matter. He coined the term atoms from the Greek word atomos, which means uncuttable. So therefore, the idea of an atom started with Democritus. Democritus' idea that matter was made up of atoms was not taken very seriously. Then, an English school teacher and amateur meteorologist came along in 1803 and put together the available experimental evidence that supported this idea. That is John Dalton. He proposed an atomic theory of matter with the following points. 1. Matter is made up of extremely small, indivisible particles called atoms. 2. All atoms of a certain element are identical. Atoms of one element are different from the atoms of another element. The joining of two or more elements forms compounds and is called a chemical reaction. Chemical reactions only rearrange, not change or destroy the atoms involved. Dalton's model of the atom described the atom as the smallest indivisible particle of matter. Note that Dalton's model of the atom still retained the idea that atom was indivisible. There was nothing that was smaller than the atom. During Dalton's time, there was no way of experimentally verifying the assertions in his theory. So nothing was smaller than the atom. So this is John Dalton, and this is his model, the indivisible atom. In 1897, while investigating the passage of electric current through a gas, an English physicist named Joseph John Thomson discovered that the gas emitted rays that were made of negatively charged particles. Since the atoms in the gas had no electrical charge, Thomson wondered where the negatively charged particles could have come from. He concluded that they could only have come from within the atom. The atom is not divisible. It is made up of even smaller particles. He named these negatively charged particles corpuscles, but today we know this as electrons. Thomson's discovery of the electron proved that the atom was made up of even smaller particles. Thomson's model of the atom consisted of a positive material scattered with negatively charged particles. He compared his model to a raisin bread just like this one. Thomson's discovery of the electron proved that the atom was not indivisible as Dalton thought. The atom is composed of even smaller particles, one of which is the negatively charged electron. This finding, however, created another problem. How can a neutral atom have negatively charged particles within it? Are there also particles within the atom that balance this negative charge? To explain the fact that atoms are neutral, Thomson referred that there must also be positively charged particles inside the atom that balance the negative charge of the electrons. But no matter how much he tried, Thomson did not find these positively charged particles. Even if he did not find the positive particles, Thomson was convinced of their existence, so he included them in his proposed model of the atom. This is sometimes called the plum pudding model, but we can use the more familiar, which is the raisin bread model. According to this model, the atom was made of a positively charged material spread out in this positively charged material were the negatively charged electrons. So this is J.J. Thomson, and this is his model of the atom. Thomson's model accounted for the existence of negative and positive charges within the atom. The positive and negative charges were spread out throughout the atom. But was this really the case? How did he know how these particles were arranged if he could not see the atom? The problem is similar to this situation. Suppose that there were marbles under your bed. You do not know exactly where they are or how they are arranged because if it is dark under your bed. Can you get an idea of how the marbles are arranged by throwing smaller marbles at them, hoping to hit them? How would you know that the marbles are in a particular area under your bed? What would you think if some of the marbles you threw bounced right back? In 1910, Sir Ernest Rutherford, also an English physicist, and his associate Johannes Geiger and student Ernest Marsden conducted a similar experiment in Rutherford's laboratory, working with real atoms. Instead of marbles, they shot a beam of very fast-moving positively charged particles known as alpha particles toward a very thin gold foil. They were hoping to find out how the particles in the gold atom were arranged. Around the gold foil was a zinc sulfide screen which flashed briefly when hit by the alpha particles. This allowed the path followed by the particles to be observed. What did they find out? If Thomson's model was correct, and the positive charge was uniformly distributed throughout the atom, the alpha particles should pass through the gold foil without being deflected. The results were as follows. Number 1. As expected, most of the alpha particles, that is 99.9%, went right through the gold foil. Number 2. Rutherford was surprised that there was a small number of alpha particles that were strongly deflected from their paths. Number 3, there were even a few that bounced right back. If you were Rutherford, what would you conclude if you got these results? The third result was unexpected. In Rutherford's own words, it was about as credible as if you had fired a 15-inch shell at a piece of tissue. Clearly, Thomson model cannot be used to explain these results. Rutherford model of the atom consisted of a positively charged center, known as nucleus, which also contained most of the atom's mass. Around the nucleus orbited the negatively charged electrons. Rutherford's model of the atom consisted of a small, dense, and positively charged center, which he called nucleus. The nucleus contained most of the atom's mass and all of the positive charge. Distributed in the space surrounding the nucleus were electrons. These were too light to have any appreciable effect on faster and heavier alpha particles. So here is Sir Ernest Rutherford's model, which is the atom's massive center. Although Rutherford's model was a great improvement, it still needs some refinements. In particular, the model did not specify exactly where the electrons were. A Danish scientist, Niels Bohr, proposed a refinement to this model in 1913. In Bohrs Model, the electrons move around the nucleus much like the planets revolve around the sun. For this reason, It is called the planetary model of the atom. The electron's orbits are known as energy levels and are located at specific distances from the nucleus. An electron cannot just orbit at any distance from the nucleus. It must be in one of these energy levels. If oppositely charged particles attract each other, why is the negative electron not drawn into the positive nucleus? To fall into the nucleus, the electron would have to lose energy. Bohr hypothesized that the electron in a certain energy level has a fixed amount of energy and is normally stable. If it does move, it is only to the next higher or lower energy level, and only by gaining or losing just the right amount of energy. These restrictions in the electron's motion keep it from falling into the nucleus. So, Bohr's model of an atom placed the electrons in orbit at specific distances around the nucleus. So again, this resembles the way in which the planets revolve around the sun. So this is Niels Bohr and his planetary model. The development of the atom model did not stop with Bohr's model. This model did quite well in explaining the behavior of simple elements like hydrogen. For more complex atoms, this model proved insufficient. Refinement to Bohr's model are based on the theory of quantum mechanics, which was proposed by Schrdinger. In Bohr's model, it is possible to determine the exact position of the electron at any given time. But based on quantum mechanics, finding the exact location of the electron around the nucleus is impossible. The quantum mechanical model of the atom states that the location of the electrons around the atom cannot be precisely determined. The region where the electron can probably be found is known as the electron cloud. At best, scientists can provide a plot showing certain regions where the electron would probably be found. The quantum mechanical model of the atom still has the nucleus at the center. Around it is the electron cloud with enough electrons to make the atom neutral. The electrons are still located in energy levels, but instead of being fixed paths, the energy levels are now the regions that make up the electron cloud. So here is Schrdinger, and here is his quantum mechanical model. Modern chemists, with their different ideas about atoms, came up with different postulates and theories that describe the structure of an atom. Later on, some chemists became well known in their contributions to the study of atomic structure. The nuclear model of the atom proposed by Rutherford in 1912 is still the picture of the atom that we hold today. Observations made afterward in experiments concerning the atom support the model. Atoms are best described through different atomic models. After a series of experiments and observations, the models have revealed the composition of the atom. Atoms are made primarily of three subatomic particles, namely proton, electron, and neutron. Protons has an electric charge of +1 and is said to be stable by itself. It is a fairly heavy particle and resides in the dense nucleus of an atom. Neutron has no net electric charge. Both proton and neutron make up the nucleus of an atom. Nucleus is located at the center of an atom. Almost all of the mass in an atom is made up of protons and neutrons in the nucleus. The electron has an electrical charge of -1. Electrons are smaller than protons and neutrons and are found revolving somewhere around outside the nucleus because their mass is approximately 1:1836 of the mass of proton. An atom is whole, but
Its various components are subsystems dependent on each other for its existence and function. The atom cannot exist without its components. The components cannot exist without each other.
At this point, let us have a short quiz. We will call this as Matchy Matching. All you have to do is to determine the name of the model which was proposed by the scientist. Flash on the screen on your left. Okay. Okay, for our answer, number 1 is letter B. The atom's massive center was proposed by Ernest Rutherford. Number 2, we have the quantum mechanical model by Erwin Schrödinger. Number 3, Niels Bohr model is called the planetary model. Number 4, J.J. Thomson's model is called the plum pudding model or the raisin bread model. And the indivisible atom was proposed by John Dalton.
Thank you for watching this video lesson. For more updates, don't forget to subscribe and hit the notification bell. Kamawa.